-4 degrees Celsius is needed to cool 110 kilograms of vegetable in a bunker for 24 hours. The initial temperature of vegetables is assumed to be 30 degrees Celsius. It's also assumed that the average temperature inside the bunker is 7 degrees Celsius within a 24-hour period. If the heat gain per hour in the bunker is 30% of the heat removed to cool the vegetables, from 30 to 7 degrees Celsius, what would be the required mass of ice? Note, a specific heat of ice is 1.935 kilojoules per kilogram Kelvin. A specific heat of vegetable, 3.35 kilojoules per kilogram Kelvin. A specific heat of water, 4.186 kilojoules per kilogram Kelvin. And the heat of fusion of ice, 335 kilojoules per kilogram. Okay, as we can see, the ice is used to cool down the vegetables, meaning the heat removed from the vegetable is absorbed by the ice. So we know the ice will melt. So we have a combination of sensible and latent heat. While for the vegetable, it only involves a change in temperature, meaning it is only sensible heat formula in the case of the vegetable. And this will be the formula to be used. And the question here is the required mass of ice. So we should find this. So for the mass of ice, it's equivalent to, for the Cp of water, that is 4.186 times the change of temperature of water. Okay, so our ice will melt into water, and the final temperature or final state of our ice, which transform into water, will also be the temperature inside the bunker. So the water temperature is also the bunker temperature, which is 7. The change of temperature, meaning it started from 0. For the latent heat of fusion, that is 335. And for the Cp of ice, that is equivalent to 1.935. And the change of temperature of ice, if we start from 0, because that's the freezing point, and our initial temperature of our ice is -4. That would be minus -4. So the unit inside is kilojoules per kilogram. For the mass of the vegetable, that's equivalent to 115. Cp of vegetable, that is 3.35. And for the change of temperature of vegetable, that is initially 30. And the final temperature is also the temperature inside the bunker, which is 7. That is change in Celsius or change in Kelvin. So the unit of our mass of ice is kilograms. What is our mass of ice required? That is equivalent to 23.82. That is in kilograms. A simultaneous generation of electricity and steam or heat in a single power plant, it is also called cogeneration. A refrigerator is 2 meters high, 1 meters wide, and 1 meter deep. The overall heat transfer coefficient is 0.532 watts per square meter Celsius. How many kilograms of 0 degrees Celsius ice will melt per hour if the inside temperature is maintained at 10 degrees Celsius while the surrounding air temperature is at 35 degrees Celsius? Okay, so as we can see, there are ice inside the refrigerator. And so you can see here, the refrigerator is maintained at 10 degrees Celsius, but the surrounding air temperature is 35 degrees Celsius. So meaning there is a tendency that heat will enter the refrigerator because there is a temperature difference. So if the heat happens to enter inside the refrigerator, it will be absorbed by the ice, which will make the ice melt. So the question here is, how many kilograms of ice will melt? So our formula to be used, it is the heat absorbed by the refrigerator is equivalent to the heat transferred to the ice. So since we have a given overall heat transfer coefficient for the refrigerator, we could use the general formula for the heat transfer, that's UA delta T, where A is the total surface area exposed in the refrigerator and the delta T is the change in temperature. While for the ice, since the process is melting, so that is latent heat because there is an involved change in phase. Okay, so let's use the given. Okay, let's start with U. So that's equivalent to the overall heat transfer coefficient 0.532. That's watts per square meter Celsius times the area, meaning that's the total surface area exposed in the refrigerator. As you can see, the dimensions are given. So let's use the formula for the total surface area for a refrigerator given the length, the width, and the height. So that is twice of the sum of all the combination of the rectangular faces. So let's start with the combination of the height and the width. That will be 2 times height times width, that is 2 times 1.2, plus for the width and the depth, that will be 1.2 times 1, plus another combination, that's the depth times the height, that will be 1 times 2. We have a multiplier of 2 on the outside because the opposite faces of a rectangular prism have equal area. So that is in square meters. And the change of temperature, that is 35 minus 10. Cancelled. Square meter is also cancelled. It's equal to mass of the ice, which is unknown. That's the latitude of fusion, that's 335 kilojoules per kilogram. And let's check the units. On the left side, the remaining unit is watts or joules per second. And on the right side, we have kilojoules. So to make this balance, let's convert kilojoules into joules. So we know that 1 kilojoule is 1,000 joules. Cancel. So the remaining unit of our mass of ice will be kilograms per second. But if we are to inspect our problem, what we need here is the number of kilograms per hour. So meaning the answer here must still be converted into kilograms per hour. So we must multiply this by 3,600 seconds in 1 hour. What is our answer? It's 1.60 kilogram. Is one whose pressure is higher than the saturation pressure corresponding to its temperature. It is also called the compressed liquid. A vapor compression refrigeration system is designed to have a capacity of 150 tons of refrigeration. It produces chilled water from 22 degrees Celsius to 2 degrees Celsius. Its actual coefficient performance is 5.86, and 35% of the power supplied to the compressor is lost in the form of friction and cylinder cooling losses. Determine the condenser cooling water required for a temperature rise of 10 centigrade. So we are asked here for the cooling water requirement in the condenser. We know that the cooling water absorbs the heat rejected in the condenser. And since there is a temperature rise, so the condenser load is the sensible heat, which is mCp delta T. And the question here is the cooling water requirement or the mass flow rate. We already have our CP of water, that's a constant, and we have the temperature rise. So meaning, to be able to solve the mass flow rate of the condenser cooling water, we must solve first the heat ejected. So for a refrigeration system, take note, the heat ejected is equivalent to the sum of the capacity and the compressor work. Okay, so we already have our QA, which is the capacity of 150 tons of refrigeration. What we don't have here is the compressor work, but we have a given actual COP. And take note, COP is equal to QA over work of the compressor. So manipulating that equation, our work of the compressor is equivalent to QA over COP, which are both provided in our problem. A QA plus work of the compressor, we can solve our QR. Okay, let's solve that directly. Our QA is 150 tons of refrigeration. Let's multiply that by 3.5167 to make that kilowatts. Okay, plus our compressor work is QA over COP, which is still 150. That's 3.5167, that's in kilowatts, over the coefficient of performance, which is 5.86. So the whole left side is in kilowatts or kilojoules per second. It's equal to the mass of our cooling water. CP is 4.187 kilojoules per kilogram Kelvin. And our rise in the temperature is 10. Take note that the change in Celsius is also the change in Kelvin, and kilojoules is cancelled in the left and in the right side. So the mass flow rate is expressed in kilograms per second. What is our answer? This is 14.75 kilograms per second. If the fluid travels parallel to the adjacent layer and the paths of individual particles do not cross, the flow is said to be laminar. Cold salt brine at an initial temperature of 0 degrees Celsius in a packing plant to chill beef from 40 degrees Celsius to 5 degrees Celsius in 18 hours. Determine the mass of the brine in kilograms per second required to cool 1,000 beefs at 250 kilograms each if the final temperature of the brine is 3 Celsius. Specific heat of brine is 3.76 kilojoules per kilogram Celsius, and SG is 1.05, while the specific heat of the beef is 3.14. Okay, in this problem, the cold salt brine is used to remove heat from the beef, meaning the heat removed from the beef is absorbed by the cold brine. So in formula form, the heat from the beef rudder goes to the brine. And since they both involve changes in the temperature, so the formula to be used on both brine and beef heat are both sensible heat. And the question here is the mass of the brine. So we must find the mass on the left side. So for the mass of the brine times CP of brine, and that's 3.76. Again, the specific heat is MCP delta T times the change of temperature of our brine. So initially, our brine is at 0, and the final temperature is 3. So this will be 3 minus 0. And for our right side, the mass of the beef, so there are 1,000 beef, and there is 250 kilograms on each one. For the CP of beef, that is 3.14 kilojoules per kilogram Celsius. And for our change of temperature, so it is required to chill the beef from 40 to 5. And this process goes on in a span of 18 hours. So we must multiply this by 3,600 to make this per second. Kilograms cancelled. as well as the change in Celsius, as well as the kilojoules. So meaning the unit of our mass will be in kilograms per second. What is the mass required for the cold salt brine? The answer is 37.59 kilograms per second. What is the apparatus used in the analysis of a combustible gas? Okay, so we have here distillates, which are to be cooled from 21 up to -12 degrees Celsius. So first, let's visualize the process. So we started at our liquid form, which is oil, at the initial temperature of 21 degrees Celsius. And our goal is to cool it down to -12 degrees Celsius. But take note, at some point during our process, our oil must be separated to its solid form, which is wax, which is at 15 degrees Celsius, meaning we should cool it down first at that temperature. Because at 15 degrees Celsius, our oil will solidify into wax, but still at the same temperature. So meaning there is a change in the phase, but there is no change in temperature. And that's what we call latent heat. And that wax is 12% of the total weight of our distillate. So for the remaining 88%, it is still at its liquid form, which is oil. And that oil is to be cooled down to our final temperature, which is -12 degrees Celsius. Same goes with our wax. Okay, so this involves changes in the temperature, but there's no change in phase, which is sensible heat. And there's also changes in the phase, but there is no change in temperature, which is latent heat. Okay, so for our sensible heat, we have a formula, mCp delta T. And for our latent heat, that is mass times latent heat. So for the two heat, we need the mass. So as you can see, what we have here is 4,000 liters, which is obviously volume. So to get the mass, it is equivalent to density times volume. So our mass is equivalent to our density, which is the same as a specific gravity times density of water. That will be 0.87 times the density of water is 1 kilogram per liter times our volume, which is 4,000 liters per hour. And it is best that we convert this per second. So we know that in 1 hour, there are 3,600 seconds. We can cancel out hour as well as liters. So what's our mass in kilograms per second? So this is 0.97 kilograms per second. And now we can proceed with our solution for the capacity. So for our Q, that will be oil at 21 to oil at 15, so that's sensible heat. So that is M times Cp of oil, which is 2 times the change in temperature, 21 minus 15. Plus, we have here oil at 15 and oil at -12 degrees Celsius. So that is still sensible heat, mCp delta T. But in this case, our oil is now 88% of our weight. So we have here 88% times mCp, which is still 2, times the change of temperature, 15 minus -12 plus. So we have here oil at 15 and it changes to wax at 15. So there is no change in temperature, but there is a change in phase. So that is latent heat. And that is composed of the 12% of its weight. So that is 0.12 times mass times latent heat, which is the mass is 0.97, and our latent heat of fusion is 290. Plus, we have wax here at 15, and we have wax at -12. So there is no change in phase, but there is a change in temperature. So again, this is sensible heat. And again, the weight is only 12% of our total. So that will be 12% times M of our oil, which is 0.97, times Cp of our wax, which is 2.5, times the change of temperature in our wax, which is 15 minus -12. So if you put that in our calculator, what will be our answer? So our answer here will be in kilowatts. So whatever our calcu give to us, that's not yet our final answer, because what we need here is our capacity in tons of refrigeration. But take note, we have here losses which are 10%. So meaning for a refrigerating machine, we must overcome the 10%. So we have still a multiplier of 1 plus 0.9, which is 1.10. And then we should also convert this into tons of refrigeration. So take note, 1 ton of refrigeration is equivalent to 3.5167 kilowatts. What is our final answer in tons of refrigeration? The answer is 31.08 tons of refrigeration. What is a clockwork operated device which records continuously the humidity of the atmosphere? That is hygrometer.